Ladies and gentlemen, welcome back for another round. This is Mr. Dool, and I thank you for tuning in. Today what we're going to do is we're going to take a look at state changes and associate that with heating and cooling curves. And so what I've got drawn on the screen here is just a big heating and cooling curve. Now, you're going to draw this. You're going to pause this and draw this in your notes. I need you to make this huge. Like, even if you have to turn your paper long ways and actually draw this thing out, we are going to add so much stuff to this, right? You need a lot of room to be able to do it, all right? So just get the general gist of it down. Notice the axes here are temperature and heat energy. And notice I've got increase in temperature, flat line, increase in temperature, flat line, increase in temperature. You want to make sure that you get all of those particular things down. All right, and then I've drawn in solid, liquid, and gas. So go ahead and pause the video, get that stuff down, and then we will begin our discussion. Okay, so to go from solid to liquid, I hope that you understand and I hope that you remember that if I'm heading in this direction, I am melting, and if I'm heading in this direction, I am freezing. All right, and so just our general state changes, and then to go from liquid to gas, if I'm heading in this direction, I am called vaporization. Now, some of y'all may know that term as evaporation. Evaporation happens passively. Vaporization happens when we purposefully put heat in, and so since this is a heating curve, then we are going to purposefully be putting heat in, and so it would be called vaporization to be technically correct. All right? So just understanding the difference between the little nuance between vaporization and evaporation there. All right? And then if I'm coming back in the other direction, we call that condensation. Condensation, all right? So those are my state changes that are going to be in this particular heating and cooling curve. All right? Now, the other thing that we have to understand, and hopefully this is just inherent, that if I'm going in this direction, I am adding heat energy, right? And since I'm adding heat energy, it is an endothermic process. All right? Now, the other part of that is if I'm heading in this direction, I have to remove heat energy, and that would make it an exothermic process. And so that's something I need you to tackle and go ahead and wrap your head around, is that when I take, for instance, a gas and it condenses back to a liquid, I had to remove heat energy from that gas, right? And the fact that I'm removing it from my substance makes it an exothermic process because that heat energy goes into the surroundings. All right? So make sure that you kind of wrap your head around that. It'll make the rest of this a little bit easier. All right? Okay, now, a couple of things. First, I need to notice where I've got temperature changes and where I do not have temperature changes, because that's going to dictate the type of energy change that it actually is. So in my vertical areas where I'm just in the same state, I see an increase in temperature here. This is a change in kinetic energy, and so I'm going to say delta KE. Same thing for a liquid, right? Where I have an increase in temperature, I have an increase in kinetic energy, or if it's decreasing, it's a decrease in kinetic energy if we're going the opposite direction. All right? So we need to understand, because remember, kinetic energy and temperature are related in the fact that temperature is just a measure of the average kinetic energy of the molecules, right? And so if I'm changing temperature, I'm changing kinetic energy. And so now the question becomes, well, Mr. Newell, what the heck is going on when I'm in this flat region? Because I don't have a temperature change. I don't see any temperature change there. And so what's going on, and what's happening here, is this is a change in potential energy, right? And so in my flat regions, these are changes in potential energy. If you're doing that in these potential energy change regions, in that flat region, you are actually overcoming the intermolecular forces between molecules to spread them out. Right? And so you need to understand, as I increase the temperature here, my kinetic energy increases, but the distance between molecules does not necessarily increase. All right? The distance changes in this potential energy area, and if you refer back to our bonding situation, you remember that the force of attraction and repulsion, as these molecules get closer, right, I'm removing energy. As they get further, I'm adding energy. Right? Okay. And so this will lead us into, since these are potential energy changes, the thing that I understand is I go back to an energy diagram. Potential energy changes have to do with enthalpies, right? So those potential energy change regions, if I wanted to actually calculate the amount of heat energy that it's going to take to do that, then what I do is I have an equation. Q is equal to delta H, and for this one to be delta H of vaporization, since it's vaporization, times the number of moles. And so if I wanted to calculate how much heat do I have to put in to actually boil 5 moles of water, I would have that value, right? These enthalpy of vaporizations, just like all my other enthalpy values, they are a table value. And so enthalpy of vaporization tells us the definition of this enthalpy of vaporization term is how much heat energy must put in to vaporize 1 mole of substance. All right? And so just like all my other enthalpy values, it is a molar value. It's a molar value. Now over here on the other end, where I'm melting and freezing, it's the same equation, but my enthalpy value is now the enthalpy of fusion. It's still times moles because it's still an enthalpy value, and it's a molar value. And so I need to understand in these flat regions, these potential energy changes, it's an enthalpy because it's an enthalpy change because it's a potential energy change. All right? And so now I jump into where I'm actually having a kinetic energy change, right? So how much energy, how much heat energy does it take to go from here to the beginning of my state change, right? And so what we're using there is we will actually use Q equals MCAT. And so this is a calorimetry problem, right? Where M is mass, C is the specific heat capacity of the particular substance, right? How much energy do I need to put in to change the temperature of 1 gram of substance, right? And then my delta temperature. What temperature am I going to change from and to? Okay? All right. So this is heat energy because this is a kinetic energy change. This is just a temperature based, right? I've got a change in temperature, so I'm going to use the Q equals MCAT equation. And if you read that, Q equals MCAT is the way that it spells. All right? And then so the same thing for all of my areas where I've got a temperature change, it's a Q equals MCAT type of problem to figure out how much temperature or how much heat energy is going to take to move your substance from one spot on that curve to another. All right? Okay. So at this point, ladies and gentlemen, we've got a lot of what we need in this particular graph. We added quite a bit to it, but please understand, right, these enthalpy values, right, the definition of these guys, you'll need to know enthalpy of vaporization. How much heat energy does it take to change the state of 1 mole of substance from, and if it's vaporization, from a liquid to a gas. For enthalpy of fusion, how much energy must be put in to change the state from solid to gas of 1 mole of substance. So remember, and it makes a difference to remember with these, which one is a potential energy change, which one is a kinetic energy change, because that dictates the type of equation I'm actually going to use, right? Enthalpy is a potential energy change. Q equals MCAT is a kinetic energy change because I actually have changes in temperature. All right? Okay. Everybody all right? Okay, and that's really it, ladies and gentlemen. There's a couple other little nuances. I think if you remember up here that temperature is a measure of average kinetic energy, I think that'll help kind of classify and clarify some of these things here about when it's appropriate to use Q equals MCAT versus when it's appropriate to use Q equals delta H times moles. All right. The other thing, just remember, enthalpy is the molar value. We see all these different kinds of things, right? And so I have to understand that if I had, in this particular situation, if I had half of a mole of water, it would be half of the enthalpy of vaporization, right? Since it is a molar value. And this is where we start to get into the fact that I'll say, hey, I got 5 grams of water, right? How much heat energy do I need to put in to boil 5 grams of water? Well, to figure that out, you'd look up the enthalpy of vaporization of water, right? And then you would figure out, you go 5 grams of water to moles of water, and then you could multiply out and figure out that amount of heat energy, okay? All right, so if you have any questions, ladies and gentlemen, make sure you get it down. Otherwise, I will see you in class.